Okay. So we've already established that this problem has a continuous function, so we should be able to write one moment and one shear equation for it. And you can see, to kind of answer Mr. Romero's question before, see, I'm going to cut this not at some distance, a fixed distance. I'm going to cut it at an arbitrary distance, x. So now we're looking at whether you want to work the left side or the right side. So we can spend just a second talking about that. So what advantage does the right side have? Cutting a section here and finding the internal forces. What advantage? Well, the right side doesn't have any reactions. You don't have to find the reactions. That could be a positive thing. But look at the resulting load. It's trapezoidal. That can be a little tedious to calculate. The left side is just a triangular shape, which won't be too bad, but we have to find the reactions. But I think you guys are pretty good at reactions, so let's try that. Let's work the left side. So to start the problem, I'll find my reaction. So there's my free body diagram, 20 feet long. I'm going to assume that I have... Now I'm going to start talking about shear force and bending moment. So I'm going to write my reactions here in terms of shear force and bending moment. So on the left side like that, a positive shear force is up, and a positive bending moment looks like that. Okay? Now I have this triangular load, and to make it a little easier to deal with, I'm going to turn that into a concentrated equivalent force, which is equal to what? The area under the triangle. I left off my height here. So what's the area of a triangle? Yeah, so 1/2 base, which is 20, times the height, which is 2 kips per foot. So it looks like the 2's cancel and you get, looks like 20 kips. I'm sorry I kind of jammed that all up in there. Now what's the distance to that force from A? Remember the centroid of a triangle?
2/3.
Yeah, it's 2/3 of that. So 2/3 of 20 is going to be a very strange number. So I'm just going to leave it in fraction form right now. So it'll be 40 thirds. It's easier for me to write it that way than whatever it would be, 16.666667 or something. Okay? So now I'm going to sum moments about A. Make sure they're in equilibrium. So what kind of moment, when I sum moments using this sign convention, this moment now becomes negative. So I have minus M. My concentrated equivalent force about A creates positive or negative moment. Negative, so I have negative 20 kips times this moment arm, which is 40 thirds. So it looks like my moment is negative, and I don't know what that is. Somebody help me with that. 800 divided by 3 is 266.7. And that would be kip feet. Okay? And then what do I do? Yeah, let's sum forces in the y direction. I'll assume up is positive. And when I do that, I've got my shear force, which is acting up, and this 20 kip force, which is acting down. That's not so bad. So shear is just equal to 20. So it looks like I've got a positive shear force at A and a negative bending moment at A. Those should factor into my equations, right? In fact, my equation should predict when x is equal to 0 that I do have a bending moment of minus 266.7 and a shear force of 20. Okay? So now let's go to the free body diagram for our cut section. So I'll assume beam has some depth, and now we're going to say it's of some length x. Now I'm going to apply my shear force, which I found 20 kips, and my bending moment, which I found 266.7 kip feet. Positive shear force, negative bending moment. And then I have a portion of the triangle that I need to deal with. And then, of course, at the cut, I have positive shear force and positive bending moment. That look good? Now what I have to work with now is how am I going to resolve this triangular shape into, like we did up here, a concentrated equivalent force. Well, first of all, for a given distance x, what's the height of the triangle? There's a couple ways to do this. You can find the slope of this line. What is the slope of this line, by the way? Rise over run. What's the change in height? 2. And the change in length is 20. So it looks like it's 10 to 1. So for every foot I go in this direction, I only go up a tenth. So if I went x feet, how far would I go up? X over 10. So that value right there should be x over 10 and should have the units of kip feet when you're done. Now you can check that. When x is 0, what do you get? 0. When x is 20, the equation says you get 2. So it matches. For a straight line, you only have to match 2 points and you have a good equation. So really what I have here is an equation that describes the loading. Okay? So now from this point, your hard work is almost done. So now, the concentrated equivalent force, I'll just call it F1. Let's go over here and compute what F1 is. It's a triangle. So what is the area of a triangle? 1/2. What's the base? X. What's the height? X over 10. So now that force is what? X squared over 20. So now I know this force is a function of wherever I cut at x. Now I'm probably going to sum moments here at the cut, so I probably want to know this moment arm. What's the centroid of a triangle from the big end? 1/3. So what is the distance? X. So this should be x over 3. Now for my money, this problem is done. If you can create this free body diagram, that's the hard work. That's where you had to think. The rest of it you don't have to think. Now it's time to get out your little monkey and grind the wheel and do your statics equations. Right? So what's the first one we always do? Sum moments. So there's my sign convention. And now I'm going to sum the moments about the cut and make sure they're in equilibrium. So let's do that. Starting on the right-hand side with this sign convention, right-hand rule, this moment is positive. What's the moment due to the concentrated equivalent force? Positive. Positive moment.
Oh, yeah, that's right. Yeah, just positive.
And the force is x squared over 20, and the moment arm is x over 3. So just so you see that, I'll write here force times distance. Now I'll slide over and look at this force, which was up. What kind of moment does that create about the cut? Negative. So that force is 20 kips. And what's its moment arm? X. And then finally I have the reaction moment, which again with this sign convention is positive. You see that? So all I do now is solve for moment. So moment now has a function of x is equal to, I'll put this in brackets so I can keep the units straight. Usually when I write these equations, I like to write the higher order terms first. So I'm looking at this first term. This is x cubed over 60. And when you move it to the other side of the equation, it becomes negative. This term becomes positive, so that's plus 20x. And this term becomes negative. And the brackets will just let me say that all those terms have kipped feet. So there's my equation for moment. Does it work? Most of the time you can check it. For example, when x is equal to 0, what's the moment? This term is 0, this term is 0. Look, it says negative 266.7. And what is the moment at x equals 0? We've already found it. Negative 266.7. So that's great. What do you think the moment at the free end here is? Zero. There is no moment at the free end. There's nothing there telling it to rotate. So that means if I plug in x equal 20 into this equation, I should get 0. So why don't you check that for me? So we've already checked that when x is equal to 0, we get negative 266.7 kip feet. So now what is the answer when x is equal to 20? So this is good. Goes to 0? Oh, I love it when a plan works. So I checked both of those. So those are both good. So now I have equation for the moment, and I can find the maximum and I can find the moment at any distance x I wish. Isn't that cool? Now let's find the shear force. So if we sum forces in the y direction, make sure they're in equilibrium. Look at my free body diagram. I'll start here on the right side. So I've got shear acting down. I've got my applied force acting down. My applied force was x squared over 20. And I have 20 acting up. That's it, right? So what's left? Solve for the shear. So the shear as a function of x is now going to be equal to minus x squared over 20 plus 20, and that should all have the units of kips. Do I know the shear anywhere? Where? At A. So the shear when x is equal to 0, which is A, according to this equation is 20. And that's what we solved for. So that's good. What's the shear at x equal 20? What's the shear out here on the free end? Well, if you put in 20 here, you'll find that it's 0. And that should make sense. There is no shear at a free end. This end is free to move up and down. What's going to stop it? Nothing. There's no shear there. Pretty cool, huh? Now, you guys are smart. Look at this equation and look at this equation. There's a relationship there. Yep. If you take the derivative of the moment with respect to x, it looks like you get the shear. Now that's just an observation now, right? That could just be coincidence. Well, later in the course, if not today, definitely Thursday, I'll show you mathematically that this relationship is true, and that we'll be able to use it. Which is great for you, because if you calculate the moment equation and you take the derivative and you don't get your shear equation, then you made a mistake. If you feel really comfortable that your shear equation is right, then check your moment. More likely the moment equation is a little more difficult to do than the shear. So this is really a self-checking problem. You usually know in conditions where you can check it at least 2 places, and then you have this relationship between them. So you should probably never leave one of these problems questioning whether you got it right or wrong. You either know you got it right, or you just can't figure it out. You won't give me a wrong answer and say, oh, it's right. No, you should be able to check. Now, you may not be able to get it for other reasons. I mean, if your free body diagram is wrong,
You may not be able to get it.
you have equations that's good for that free body diagram, but it may not be appropriate for this problem. Okay? Let me stop this thing, and we'll work another one.